Hi all, welcome to 8th lecture of Robotics and Controls, and today we are going to discuss Jacobians. So in today's lecture we'll introduce the topic Jacobian. But before starting the lecture, let's see what we studied in our previous lecture. So till now we have studied the forward kinematics and inverse kinematics of manipulators. And in the last two lectures, we have studied forward kinematics and inverse kinematics of differential drive. We also saw some of the Python codes to implement these forward kinematics and inverse kinematics to develop some animations in the Python. And now let's move on to what are Jacobians. So Jacobians are just a fancy word to represent gradient of a vector valued function. So let's see what is gradient. I hope you all know just what is a gradient. So let's say f is a function from r n to r. So basically it means if it takes n inputs and gives one output. So for example, um, y equals fx1 comma x2 to xn, and y belongs to the real set, and uh, xi belongs to real set for all I equal to 1 to n. Okay, so if we have this is called a real valued function because the output is just a real number. So if we take the gradient of this function with respect to all these values, so let's say I'll call this f q, where q is um, x1 x2 xn. So where q is a vector. Okay, so if I want to find the gradient, then the gradient of the function can be represented as a um, del of fq, and basically it is given by del f by del x1 comma del f by del x2, so on and so forth, del f by del xn. Okay, which actually tells that a gradient of a real valued function is a vector. So del f belongs to Rn. You can see it is a vector. All right. So keeping this in mind, let's see what is a Jacobian. So Jacobian is just a gradient of vector valued function. Okay, so what do I mean by vector valued function? I'll just explain it. All right. So what is a vector valued function? We saw in the last minute that real valued function is a function which gives a real number as a output. So vector valued function is a function that gives a vector as an output. So any function f which takes n input and gives me m outputs, so it's a vector rather than a scalar. This is called vector valued function. All right. So how does it if we write f equals f1 q f2 q all the way till fmq, where q is a vector of real numbers xm. So here here y belongs to Rm, the output, and q belongs to Rm. Alright, so this is a vector valued function. So if we want to find out its gradient, it's called the Jacobian. So how do we find the gradient of that function, of this vector valued function? So it's basically del f by del q, and because the gradient of a real valued function was a vector, the gradient of a vector valued function will be a matrix. So yeah, so the way we write it is as follows: del f1 by del x1, del f1 by del x2, so on and so forth, del fm by del this is 1 del xn, right? The second row will be del f2 by del x1, del f2 by del x2, so on and so forth till del f2 by del xn, and so on and so forth till del fm by del x1, del fm by del x2, till del fm by del xn. So you see, the Jacobian of a vector valued function is a matrix of m cross n. So m rows, basically the number of basically the amount, the number of components of the output, and n is the length of the vector of the input. So this is the Jacobian of a vector valued function. Now let's look at one of the examples. So alright, so let's so f equals, let's say, x square plus y square, comma 2x plus 3y plus 5. So let's say it's the function, and q is x comma y. Okay, so basically f here is from R2 to R2. Input is also has two inputs and has two outputs. Okay, so what is the Jacobian? So let's write the Jacobian. It will be del f by del q. It will be del f1 by del x1, or del x, del f1 by del y, del f1 by del it will be del f2 by del x, and del f2 by del y. So if we try, what is del f1 by del x is 2x, right? So this is f1, let me just write, so this is f1 and this is f2. So del f1 by del x will be del by del x of x square plus y square, which will give you 2x, right? Similarly, del f1 by del y will give you 2y, right? Because it's obvious, because yeah, it's the same as the above one, so it will give you 2y, right? So now what? Okay, what is del f2 by del x? It's 2 x plus 3y plus 5. So del y del x gives you 2, right? And del f2 by del y gives you 3, right? And with the same logic. So I'll just make it smaller. Alright, so we'll use those values here. So del f1 by del x is 2x, and del f1 by del y is 2y, and del f2 by del x is 2, and it is 3. Alright. Okay, so now let's see if we can find the value of Jacobian for a given value of x and y. So, right, so you can see now that j is a function from R2 to R2 cross 2, right? Now, what is j at 1 comma 2, which is same as del f by del q at 1 comma 2, where x is 1 and y is 2. It will be given by 2 into 1 into 2 into 2, 2, 3, which is given as 2, 4, 2, 3. So this is the Jacobian of f at the point 1 comma 2. Okay, so this is how we calculate. We'll do one more example, let's say. So this time I'll just change the lengths of the vectors and the so let's say f is given by sin x, sin x, cos x, and e to the power x plus e to the power y. Let's say it is given by cos y square. Sorry. Okay, so let's say this is the function and q is given by x comma y. Right. So what is j? Del f by del x is given by del f1 by del x, del f1 by del y, del f2 by del x, del f2 by del y, del f3 by del x, and del f3 by del y. Okay, so del f1 by del x is cos x, del f1 by del fy is 0, right? Del f2 by del x is 0, and it is minus sin y square dot 2y, right? And then del f3 by del x is e to the power x and e to the power y. So you can see j here is 3 cross 2, where 3 is the length of the vector which comes as an output, and 2 is the length of the input. So yeah, so this is what Jacobian is. So there is a method to symbolically calculate Jacobians in Python using the SymPy library. We'll look into that in our next lab video. It will be a short video in which we'll take one of the examples here and just show you how to calculate the Jacobian using the inbuilt library SymPy. See you in the Python environment in the next video. Thank you.